Asyle, the Engineer and the Island. Week 24, Day 1. The dynamo isn't even close to being finished, but I don't need to let that stop me from building some electronics. Like I said last week, I need to finally try building a radio so I can call for rescue, rather than waiting for it or taking my chances with the smugglers. It would also help if I could hear rescue coming, so some kind of two-way system would be nice. A radio receiver basically works like this. Radio waves pass through a conductive antenna and shake the electrons in it, like waves in the ocean shaking a bobber up and down. This shaking is usually very weak, so radio receivers are designed to amplify the signal so it can be heard, using either resonance, where the electron shaking builds up on itself, or a transistor to amplify the signal electronically. Because there are so many different frequencies of radio waves being used for communication, radios also need a filter to isolate just the radio channel you want to listen to. Imagine a bunch of people trying to hold conversations by tapping out Morse code on a piano, each one tapping just one key, and you can get an idea of just how noisy the radio spectrum can be without a filter. A radio transmitter kind of does the same thing, but backwards. It takes a weak input signal from a telegraph key or microphone, and amplifies it at a specific frequency, shaking the electrons in the antenna so hard that they create radio waves, again, like shaking something up and down in the water to create ripples. So that tells me what I need to build: an antenna, an amplifier, a filter, though I'm also going to need a power supply to run the thing, a microphone or telegraph key to send messages, and some kind of speaker so I can hear any responses. I decided to focus on the speaker first, because I kind of already had an idea of what I wanted to try for it. Obviously, I could have tried making an electromagnet coil to vibrate a diaphragm like a regular speaker, but wire is a precious resource to me, so I don't want to use it if I can avoid it. Instead, I wanted to try making a special crystal called Rochelle Salt, which is piezoelectric, meaning that it'll vibrate when a voltage is applied to it, and vice versa. This will allow it to work both as a microphone and a speaker, in addition to being much easier to build, in theory. I remembered that the key ingredient of Rochelle Salt was cream of tartar, or potassium bitartarate, and I also vaguely remembered that it was a byproduct of winemaking. So when I got up in the morning and started my morning chores, I checked on my ethanol distilling pot. I've basically been recycling the mash of fermenting fruit and water in it over the past several months, occasionally scooping out the stuff that refused to ferment once the pot was getting full. As a result, I found that there had been a buildup of discolored, white crystals around the rim of the pot as the levels of fluid rose and fell inside from evaporating and filling. I was able to loosely confirm the crystals to be potassium bitartarate because they were so tart, which is where I think the name comes from. Furthermore, there were grainier crystals sitting at the bottom of the solution. I remember now that potassium bitartarate crystals are sometimes called wine diamonds, because they don't like to dissolve in wine and fall out of the solution over time. Still, to collect as much potassium bitartarate as possible, once I'd cleaned out the solution a little, I decided to put the pot in the cellar freezer, as the cold temperatures should help even more crystals grow out of the solution. Probably won't be ready until tomorrow. While I was down there, I took note of how dirt and grime tended to fall to the bottom of my cellar freezer, making it a kind of gross place to store food, so I made a mental note to clean up down there later. In the meantime, I started working some clay to make another hearing trumpet to focus sounds going into and coming out of the crystal when it's finished, as I don't expect it'll be able to vibrate very strongly. I also made a smaller clay earpiece, just in case the vibrations end up being so small that I have to put the crystal right next to my ear to hear it. Next, I need to start working on an amplifier, and there are two ways I can do this: a transistor or an LC-Oscillator. I already have some ideas for how to potentially make a transistor or something similar, even under these primitive conditions, and it's an experiment I actually wanted to work on long before I came to this island. There are a lot of different kinds of transistors, but most work basically by using a small voltage to pull conductive atoms out from, or push conductive atoms in between two terminals carrying a much larger current. This is generally called a Field Effect Transistor. Most modern transistors use silicon crystals with charge-carrying elements dissolved in them like boron or arsenic, but obviously I don't have access to those kinds of materials or manufacturing methods. However, it occurred to me some time ago that moving charge carriers around like this is kind of like how electroplating moves conductive elements, like copper, to one side of an electrolytic cell or the other. I imagined that if I was magically transported back to the 1900s for some reason, this is how I would try to make transistors if I had to. And it seems like a good way to try and make transistors now. Since I was already knuckle deep in clay, I started making what amounted to a clay circuit board that I could test my transistor ideas on, carving channels in it of varying lengths and widths. The idea was that I'll fill the channels with an electrolyte, apply a signal voltage across the short side of the channels, and apply a larger voltage along the long side of the channels. Just like a field effect transistor, the smaller signal voltage should pull the ions in the electrolyte solution to one side of the channel, increasing its conductivity in proportion to the strength of the input signal. And because the resistance of the channel will drop in proportion to the signal strength, a bigger voltage across the channel will increase with it, functionally amplifying the input signal. I didn't know which sizes or shapes of channels would work best, so I carved out several and left them out to dry with the hearing trumpet for the day. This didn't take long to make, so, while I was at it, I built one more tablet with a series of parallel channels in it. My plan for this tablet was to pack the channels with charcoal or some other conductive substance later, so I can use it as a breadboard to help me prototype my circuits more easily and without having to use a lot of wire. I decided to hedge my bets and also build an LC-Oscillator, which uses resonance to simultaneously filter and amplify signals of a specific frequency, kind of the same way a flute or trumpet uses resonance to amplify a specific note from an otherwise noisy stream of air or vibrating lips, only with electricity instead. It consists of two main components: the capacitor, the C part of the LC-Oscillator, and the inductor, which is the L part for physics reasons. The capacitor is kind of like a battery which stores a very small charge, but can charge and discharge very quickly. It consists of a pair of metal plates, usually very thin, with a gap between them, usually filled with an insulator called a dielectric. The inductor is basically a wire coil, like an electromagnet, which can also store energy like the capacitor, but as a magnetic field instead of an electric field. When these two components are wired together, and the capacitor gets charged up a little by an input signal, it'll start discharging itself when the signal goes away. In order for the charges on one plate of the capacitor to reach the opposite side, however, they have to pass through the inductor, creating a current, which creates a magnetic field inside the coil. When the capacitor is fully discharged, though, the current stops, so you'd think the magnetic field would stop too. But wire coils are kind of weird, in that they don't like it when the magnetic field inside them changes, so they use the energy stored in that magnetic field to keep the current passing through them. This causes the capacitor to start charging up again, but backwards, until the inductor runs out of energy to keep up the current. The capacitor then discharges again, which magnetizes the inductor again, which recharges the capacitor again, etc., causing energy within the circuit to swap back and forth at a specific rate, dependent on the size, shape, and materials the inductor and capacitor are made from. Just like the size, shape, and materials a musical instrument is made out of determines the note it plays. This electrical vibration will damp out eventually from small resistances in the circuit, but if it keeps getting fed energy at its resonant frequency, that energy will add together and pile up, which is what allows it to function both as a filter and an amplifier at specific radio frequencies. The inductor was trivially easy to make. All I needed was a bamboo core and some wire to coil around it. I was able to finish this in a few minutes by using the lathe to make the coil. I was just a little sickened by how much wire it took though, but that's also why I tried to make the wire as thin as possible the other day. I could have tried filling the bamboo form with iron powder, but I wanted to save that for the dynamo. Most of the radio frequency inductors that I've seen use air cores anyway. The capacitors, however, were a little harder to make because I needed to make flat plates of copper, and ideally as thin as I could make them so I wouldn't waste material. I could have tried hammering the plates I had, but I wasn't confident in my ability to pull that off without eventually breaking whatever foil I tried to create. Plus, it would have had a very bumpy and uneven texture, which would have been less effective than a smooth one. Instead, I figured I could repeat the trick I did for the lead-acid battery, dipping a surface in liquid copper to give it a very thin coating, which I could then remove and use as a small square of foil. I had a little more copper ore that I needed to melt anyway, so once the kiln was warmed up, I gathered my smelting equipment again and gave it a try. Again, it took some fiddling, but I found the right technique for making good, thin films of copper on the end of a piece of bamboo. I found that the heat of the liquid metal caused the bamboo to burn slightly, creating a thin layer of coal that made the resulting thin tubes of copper easier to slide off without damaging them. This also allowed me to reuse the bamboo sticks a little, though the surface quality of the copper rings degraded with repeated use. I tried to use the largest diameter piece of bamboo I had available to me, because one problem with this technique was that I couldn't use it to make very large sheets of copper foil, only ones the diameter of my bamboo dipping stick, which I would have to patch together if I wanted to make anything larger. It wasn't that big a deal though, and I tried to make a bulk batch of them so I had plenty ready for future experiments. I didn't bother smelting my remaining iron ore, even though I had the kiln ready. It just takes too much energy to melt, so I just added the iron oxide powder from a few days ago to my electrolysis cell and had an early lunch. Next was the somewhat tricky part of making the capacitors. Not so much hard as it was fiddly, I guess. I did my best to cut most of the plates to equal sizes using a bamboo straight edge, so they would otherwise have a uniform capacitance. I held some of them back for later, in case I needed to make capacitors of specific values. I expect I'll probably need more than one value of capacitance, but 1, I can't measure that right now, and 2, I can change the way I wire them together to affect how much capacitance they add to the circuit. Once the plates were cut, the next step was to sandwich something between them, and while there were a lot of materials I could choose from, I wasn't really sure which, if any, would make the best dielectrics. So for today, instead of bulk batching a bunch of capacitors, I decided to experiment, making a different capacitor for each dielectric. Paper, carbon, latex, ammonia, water, coconut oil, creosote oil, sulfuric acid, nitric acid, ethanol, methanol, etc. For the liquid ones, I used a little paper or fabric to soak up the liquid and hold it in before dipping the plates in latex to insulate them from each other and from myself before leaving them out to dry in the sun. It has occurred to me, though, that I don't really have a way to measure which one is better. I really need some kind of electrical measurement tool. I've made my own ammeter before, using an old bathroom vent motor and some magnets, but if I try to build one out here, I won't have anything to compare the results to, and thus I'll have no way of measuring objectively how much current is flowing through my circuits. This won't be as easy as when I measured an objective meter using a pendulum, And while I could make some subjective unit of current or voltage, it would make my math harder down the road if I needed to add some conversion factor. Imperial system. So I need to figure this out now. I tried hard to think back to my college physics classes with Dr. Parker, and vaguely remembered something about the standard for electrical current being measured by putting two current-carrying wires next to each other. The current makes magnetic fields that cause them to deflect towards or away from each other with a certain amount of force. By measuring the force between them with a weight, I can calculate the current passing through them. However, this will also be complicated by the fact that the strength of the magnetic field changes with distance from its source, so as the wires deflect, they'll be changing the total forces acting on them. I can fix at least one wire in place with a guide, like a piece of bamboo, while leaving the other one free to flex a little. Then I can just hang a light weight on it until the wire returns to its non-deflected position, at which point I'll know exactly how much force it's holding up at that distance from the other wire. This, however, will not be sensitive enough to act as an effective ammeter. It'll only be useful for calibration. To build an actual ammeter, I'm going to have to build something with a bit more oomph to it. Probably some magnetic coils of my own, like I made for the dynamo. There are several issues with something like this, though, as I found out the first time I tried to build my own ammeter. The first is that the coils by themselves won't be very strong, so unless the current is really high, or I give the coils lots and lots of turns, I won't get a lot of deflection, and therefore not a lot of sensitivity. The second is that, because the coils will be weak, they won't be able to handle a lot of mechanical resistance, which means I need to make the rotating coil of the ammeter as lightweight and the bearing as low resistance as possible. Thirdly, I'll still need to get current to that rotating coil, which means an electrical contact, which will create some mechanical and electrical resistance. Fourthly, I need a way to make the coil return to its default position when the current changes, otherwise I won't actually be measuring anything. A weight would stop providing a return force after a certain amount of deflection, in addition to giving the coil more inertia, and a spring would generate more mechanical resistance the further it was deflected, probably making it the better, if more fiddly option. Finally, depending on how I arrange the coils relative to each other, the meter may stop deflecting once it reaches a certain maximum deflection. I think I can fix this by basically embedding the rotating coil inside the static coil, which gives me an idea on where to start for this meter. I built a small square frame out of bamboo and used my lathe to wrap it in wire. This way, the magnetic field experienced by the rotating coil would always be consistent no matter what. Next, I started wrapping a coil around a slightly smaller piece of bamboo that was intended to fit inside the frame to act as my rotating coil, but then I realized I had something much better: a compass. It fixed virtually all of the design problems I previously outlined: mass, recoil, mechanical resistance, etc., while being trivially easy to build and install. Almost felt like cheating. All I had to do was rebuild the frame and stator coils to be closer to the compass needle for greater effect, and I put a paper cutout behind the compass to draw on the results of my calibration, so the compass would act as an indicator needle. The result was compact, lightweight, and probably portable, like a proper multimeter, in addition to saving me a fair amount of wire compared to my original design. The only problem I anticipated having with it was that I would need to orient the ammeter relative to magnetic north every time I wanted to use it, so the compass needle would be pointing towards 0 on the dial before hooking it up to anything. But this seems like more than a fair trade-off. It hardly took an hour of building and coiling to finish the ammeter, leaving me with plenty of time and wire to build the calibration rig, which basically amounted to a single, long, thin wire wrapped around a few pegs in the wall, such that two long sections of it were parallel and close to each other. I briefly paused the electrolysis rig to use the current to power the calibration rig. There was a problem, though. The dynamo was still too weak to put out an appreciable current. Furthermore, the current it generated was a pulsing direct current rather than a constant direct current, so when the calibration wire moved at all, it wiggled up and down, so I couldn't get a good idea of how much weight it was actually bringing back to base deflection. I couldn't think of any way to fix this in the dynamo right away, so my only solution was to start charging the battery, which will definitely produce a consistent voltage and current, at least until the charge runs out. This will put my iron plating project behind a day, but I don't think there's much else I can do. Probably should have been charging the battery sooner, but again, iron plating took precedence. I finished rebuilding and refilling the battery before leaving it to charge up for the night. I still had a couple of hours left before the sun went down though, so one thing that occurred to me was that I would eventually need some resistors to help regulate current and voltage in my circuits, and it would help if I could make them pretty standardized. If I remember correctly, most of the resistors I've worked with are thin wires of varying lengths, wrapped in a material to keep them insulated, but I didn't want to waste wire, nor could I really control how thin it was. I had an idea though that I might be able to make them out of carbon by coating threads of varying lengths and thicknesses in clay and then cooking them in the kiln and adding wires to the ends. The idea is that the threads will cook, but without oxygen they'll turn to pure coal, while still retaining a consistent size and shape for a consistent resistance. Another idea I had was to do sort of the same thing, but with sulfuric acid, which will also turn the cellulose into carbon, and might give me a bit more control over the size and shape of the resulting carbon, possibly using paper instead of thread. These were pretty easy to make, and I spent the end of the day making several of varying sizes and shapes before leaving them to dry and getting ready for bed. Week 24, Day 2. I put my clay parts from yesterday in the kiln early in the morning, and after my morning chores, I checked on the potassium bitartarate. Sitting in the refrigerated cellar all night definitely aided crystallization. I poured out what was left of the ethanol solution. It occurs to me now that I could have forced even more crystals out faster if I poured more ethanol into the solution, and the bottom of the pot was covered in jagged crystals. It was so cool, I felt like an actual wizard. I could see though that they were stained reddish purple from the fig juice and the ethanol mash, when they should have been clear, so I scraped out as many of the crystals as I could and dissolved them in hot water from the solar tower, before running them through a charcoal filter to get the organic contaminants out. The resulting solution was, fortunately, clear. While I had it in that state, I decided it was time to move on to the next step in the recipe for making magic piezoelectric crystals. However, I wasn't totally sure about what that next step was, because I've seen the recipe done several different ways, using baking soda, sodium bicarbonate, washing soda, sodium carbonate, or lye, sodium hydroxide. Just that the final chemical composition of the crystals was potassium sodium tartarate. That told me though that I just needed something to get the sodium into the mix. I could have made sodium hydroxide by the electrolysis of seawater, but again, the electrolysis rig was busy. The easiest solution then was to get more sodium carbonate from burning seaweed. I was running low on washing soda for my laundry anyway, so I went down to the beach and collected what I could from what had washed up from the tide, and what I could reach easily from wading into the surf and swimming just a little bit. I couldn't swim much because I didn't want to take my shoes off and risk stepping on a sea urchin or cone snail. Still, it did get me thinking that there was a lot of cool stuff in the ocean that I could be exploring, and I again considered making some diving equipment. I put it on my mental to-do list, but at the same time, if I'm making a radio, I may not be here long enough to use it. When I got back to base, I mashed and squeezed the seaweed to get the alginate out of it for future projects, storing it in the cooler to keep it from spoiling, before putting the rest of it in the kiln to dry and burn. I hooked it up to the fractionating column just to see if the seaweed produced any interesting distillates. I also put in all the resistors I made yesterday to cook for a few hours. By that time, the battery had charged enough for me to start testing the ammeter, so I removed the battery, reset the electrolysis rig, and started running current through the calibration rig. I didn't want to waste the juice though, so I tied a string to the deflecting wire with some small knots and light sticks near the end. The higher the wire deflected, the more weight it would have to pull up. That way, I was able to almost fully calibrate it after 1 or 2 shots. It did take a little fiddling, adding and removing weights to the strings a few times, and then writing the result on my ammeter dial as the current passed through. I then measured the weight that was lifted on my scales and calculated the current using the following equations. The force acting on a moving charge is given by the equation F equals Q times V times B times sine of theta, where Q is the magnitude of the charge, V is its velocity, B is the strength of the magnetic field acting on it, and theta is the angle between V and B. The magnetic field from a long, straight wire is given by the equation B equals mu naught times I divided by 2 pi r, where mu naught is the magnetic permeability of the air, I is the current passing through the wire, and r is the distance between the wires. The magnetic field is perpendicular to the wires, and both wires have the same amount of current running through them, and I equals Q times V divided by D, where D is the distance that the current has to travel, that is, the length of the wire. So the whole equation condenses down to F equals I squared times D times mu naught divided by 2 pi r. Throw in the mass that the wire lifts, and you get I squared equals 2 pi r mg divided by D times mu naught. That squared factor complicated things, so I took a few minutes to make a modification to my linear calculator. I manually calculated several squares on a piece of paper and connected the dots, unsurprisingly a parabola. I then carved a piece of wood to match the curve and added it to the calculator frame. It's not a perfect solution, but now I can use it in place of the linear bar to calculate squares and square roots. Frankly, I should have done that a long time ago, but now that I have it, I'm quite pleased with how simple a solution it was for such an otherwise very difficult calculation to do on paper. Once I knew exactly how much current turned the ammeter dial so much, I was able to extrapolate all the current values between that and 0, and from there, all the increments beyond it. However, while I designed the ammeter dial to follow as linear a relationship to current as possible, I couldn't be certain it did so perfectly, so I got another length of wire, exactly the same length and width as my calibration rig, and made a sort of electrical bypass around the calibration rig. Because each length of wire had about the same resistance, the current going through the calibration rig was split in half between them, and I calibrated a second time. It turned out to be close enough to linear, which I found pretty impressive. Still, I calibrated both ways a few more times just to make sure. Eventually, I got a good enough average to feel confident that the ammeter was properly calibrated. At this point, I was ready for a little lunch break, and when I was done, the seaweed I had finished burning. No interesting distillates as far as I could tell. The circuit boards were also done cooking, but I set them aside for the moment. I then filtered out the sodium carbonate, setting some aside to dry into washing soda, and pouring the rest into my potassium tartarate solution, which I heated for a little while in the kiln just to make sure that the reaction was complete, before placing it back in the cellar to cool and crystallize. I suspected these crystals weren't alcohol soluble either, since the molecules should have more or less the same ends on them. So first, I reduced as much water as I reasonably could before the solution started wanting to crystallize again, before adding some ethanol to help it along. This was a tricky process because I wanted the solution to form large monocrystals rather than a bunch of tiny polycrystals, which is what would have happened if I just boiled all the water out of it. This was naturally a slow and delicate process, but to help it along, I suspended the ends of several wires in the solution and made sure that the wires were touching the cooling pipes in the wall of the cellar. These wires should end up getting cold sooner than the rest of the bowl and attract crystals to start growing on them. This should also save me the delicate process of trying to make good electrical connections with these crystals, since they'll already be stuck to the wires. I returned to my ammeter after this, and was eager to move on to testing my resistors. However, I had a slight problem, in that while I knew how much current was flowing through my ammeter, I didn't know how much voltage was coming from the battery, and I needed to know both in order to use Ohm's law to calculate resistance, V equals IR. I could use the ammeter as a voltmeter, but only if I put a large resistor of known value on it, so it was a bit of a catch-22. I spent a long time racking my brain for tricks and mathematical gimmicks to try and get around the problem, but I ultimately found that there were none. In a way, I had to cheat. As I was pacing around, frustratedly ruffling my hair and rummaging through my equipment looking for some kind of inspiration, I got what felt like a real blast from the past as I came across the remains of the emergency radio that was attached to my life raft when I first washed up here. Seems like it's been ages now. I'd completely forgotten about it. I considered trying to repair it, which would have been much easier than trying to build my own radio from scratch, but needing to be lightweight for the plane, it was built mostly using integrated circuits, which were far too small for me to manipulate or desolder using the tools I had, even if I had a clue how to fix them. I could barely break into the casing of the darn thing, which makes it that much more ironic that it apparently failed in the first place. Besides, it still kind of felt like cheating, as I was starting to enjoy the challenge of trying to build and figure out everything myself from scratch. The radio did at least have a battery of its own, which came at a standard voltage of about 1.5 volts, and it had a few exposed resistors in it of standard values that I could calibrate off of. With my vigor restored, I started by using the battery to calibrate the internal resistance of the ammeter so I could compensate for it. It wasn't much, like a few milliohms, but I wanted to make sure that my equipment was as accurate as possible. I used this information to calibrate the voltage off of my lead-acid battery, and I found that each individual cell produced about 2 volts, and by rearranging the way they were wired together, I could get the voltage up to 12 volts, which I was a bit surprised by, since that's the same voltage as a real lead-acid car battery. I guess electrochemistry is electrochemistry no matter where you are. Next, I started calibrating the resistors off the ones in the emergency radio, using the battery, with its known voltage, to drive a current through it, from which I could back calculate the resistance. It was kind of tricky because most of the resistors had colored bands to identify them, and I never bothered to memorize what they meant. I always hated that system anyway. You could just as easily write the numbers on the resistors after all. However, the known voltage from the battery helped me get close enough. As I went about measuring the homemade resistors, what I was more interested in than their actual values was how closely otherwise identical resistors matched each other. This helped me determine which manufacturing method was the most consistent. It turned out that the cooked resistors were actually the most consistent ones, which was a bit of a surprise for me. From this, I was able to make some estimates of the electrical resistivity of carbon, which was about 65 milliohms. With this information, I can manufacture more precisely valued resistors in the future. I spent some time putting this knowledge to use, building a new set of resistors that should have rounder values that I can set aside for future projects. I still had some time at the end of the day, so I decided that, just in case I needed even more precise control of my electronics, I needed to make a few potentiometers, or variable resistors. They work by basically having a long conductive film with a contact on one side and a contact you can slide anywhere in between. The tricky part was coming up with a way to keep the contact from scraping away the film, as I was planning on using carbon again. The knowledge I gained from dipping paper in sulfuric acid didn't go to waste, as I used it to create the conductive film for my potentiometers, mounting it to a bamboo cap for stability and protection. For the moving contact, I simply bent a piece of wire into a crook and attached it to a second bamboo cap that I could slide over the first and turn back and forth, also using this wire as an axle. I probably could have gotten away with letting the contact slide and scrape across the carbon, as it was simple enough to make or replace, but I decided that if it's worth doing, it's worth overdoing. So I took some of the tiny scraps of thin copper I had left over from trimming the capacitors and tried to wrap them around the crook in the sliding contact to basically make a little wheel that would roll across the contact instead of scraping it. The flakes didn't work as well as I had hoped, however, and I found it was easier to just coil a little wire around the crook instead. I found in this way that I could also vastly increase the range of values the potentiometer could cover by cutting the film into a spiral, allowing the little wheel to slide in or out as it followed the groove. It took some work and experimentation, but I'm pleased with it. Didn't have time to make more than one before the end of the day, though. Week 24, Day 3. I threw my new resistors into the kiln in the morning to cook, and did my morning chores before finally checking on my magic crystals, hopefully for the final time. What I found kind of looked like rock candy hanging from the ends of my wires, in clusters of beautiful, transparent crystals. I probably made conditions a little too good for crystallization, causing them to form quickly and thus only grow to a small size, but I found a few that were big enough for me to work with. I used an obsidian blade to carefully cut away the crystals I didn't need, leaving a singular, squarish crystal behind. The rest I poured back into boiling water to try and repeat the crystallization process, only this time I left the solution out in the open, rather than in the freezer, so that crystallization would occur more slowly, and hopefully produce bigger crystals. In the meantime, I mounted the small crystal I had in the earpiece and gave it a try, rubbing the wires on it up against the battery contact. And while the result was decidedly faint, I could definitely hear the electrical contact being made as a sound, which was pretty cool. With this, I figured I could finally start doing some tests on the capacitors I made the other day. They were definitely dry by this time, and I finished them off by wrapping them up into cylinders, so they were easier to work with and took up less space on my circuit boards. I carefully wedged some little wire leads in between the plates and the rubber coating to give them an electrical contact. As I mentioned before, capacitors are basically like little batteries, which can charge and discharge a small amount of voltage very quickly. Each one takes a different amount of time to charge, depending on their characteristics and how much current is being pumped into them, which is in turn also affected by any resistance in the circuit. This is called the circuit's time constant, and is given by the equation T equals R times C, where T is the charging time, R is the resistance, and C is the capacitance. If I can use my clocks to measure how long it takes the capacitor to charge up to the same voltage on my batteries, and I know the resistance in the circuit from my ammeter, then I can calculate the capacitance of my capacitors. I got some resistors, and in particular my potentiometer, and hooked them up to my ammeter using the breadboard, which I packed with coal. It was handy, but messy, so I'd like to make a cover for it later. I set one of my clocks nearby, and at first, I tried to count how many times the capacitor charged and discharged in a minute, watching the needle on the ammeter until it reached the maximum voltage, at which point I disconnected the battery and waited for the needle to move back down again. My hope was to average out the number of charges and discharges over a minute to get the time constant, but I found that these capacitors had such low capacitances to begin with that they charged up extremely fast, requiring me to use a very large resistance. I found it easier and faster to, instead, use the potentiometer to increase the resistance in the circuit until the needle on my ammeter ticked in time with the ticks of my clock over a minute or two. Then I measured the resistance in the circuit and back calculated the capacitance of each capacitor, which I proceeded to write on them. Of the different dielectrics I tested, I found that sulfuric acid gave them the most capacitance, which I suppose makes sense since it makes them more battery-like. I found that I could also do the same time constant trick for the induction coil I made the other day, to calculate its inductance. At that point, I had just about everything I needed to start building an LC-Oscillator radio. There was one more thing I really needed though. If I wanted to be able to tune the radio to a specific frequency, I needed to make a variable capacitor. It works like a regular capacitor, except that you can slide the plates back and forth to change their overlapping area, and thus their capacitance. The traditional way to make a variable capacitor is to mount several half-circular plates to an axle, and allow half of them to rotate with it, while the other half remains stationary. That's how you change the shared surface area. However, I didn't want to cut my precious copper plates, so I made a somewhat less space-efficient version, attaching the rectangular plates to nested bamboo caps, like the potentiometer, and rotating them to change how much they overlapped. Because the base capacitance of this capacitor would inevitably be very low, I knew it would also give me very fine control over the circuit's resonance frequency, though not a great deal of range. However, by adding more capacitors to the circuit as needed, I could bump up the range by a discrete interval. I'm guessing that's what those big buttons on old-time radios were for. Ka-chunk, ka-chunk. I finished hooking up the capacitors, variable capacitors, and inductor together in a circuit and gave it a little test with the earpiece, using simple wire contacts as switches to control how many capacitors were in the circuit. To my delight, I found that I could hear a high-pitched sound from the earpiece, and could subtly change the pitch by turning the dial on the variable capacitor. I guess it says something about me, though, when the first thing I wanted to do with this technology was create electronic music. At that point, though, I stopped for lunch, and while I probably could have used the LC-Oscillator by itself as a radio, I still considered myself only half done, because I wanted to work on making a transistor radio next. It may be an unnecessary complication in one respect, but in another it is necessary, because I can use one radio as a receiver and the other as a transmitter, and test which one works best for each function. So, I finally picked up the clay tablets I built for my transistor experiments and got to work. I started by coating the long walls of the channel with an ink that I made from charcoal dissolved in ethanol to keep it suspended. Depending on how well they work, I may try electroplating some copper onto these spots instead. Once the ink seemed more or less dry, I filled the channels with different electrolytes like salt water, potash, and sulfuric acid to see which, if any, produced the most desirable effects. I then placed wire at each of the short sides of the channels for the transistor's power inputs and outputs, and a wire on each of the long sides of the channels for the transistor's sensor input and ground. These would function like a capacitor and/or electrolytic cell depending on the polarity and voltage to which it was charged. Now, you may be asking yourself, won't the power leads do the same thing as the sensor leads, and more effectively than the sensor leads since they have more voltage? Or, why shouldn't the power leads just short through the carbon on the walls? That's good thinking. Well done, you. But because of the channel's shapes, the power leads have much more resistance, long and skinny, to pump electricity through than the sensor leads do, short and wide. So they lose more voltage along the way. And because of the electrolytic reaction occurring in the cells, conductive molecules should be pulled more to one side of the cell than the other by the sensor leads. For example, if we're using salt water, conductive sodium ions should start collecting on the negative side of the terminal, while insulating chlorine bubbles should start forming at the positive terminal, effectively creating an insulating coating on the wall there, so the power terminals can't short through it. They can short much more easily through the other terminal though, which is what we want, and we can control how easy that is by how much voltage, and by extension how many sodium ions, we pull to that side. Again, just like a field effect transistor. This also means I can pull a more sophisticated trick with these transistors and make them bipolar, which means I can flip the voltage on the power terminals if I need to, or control whether a positive or negative power voltage gets through or not, something you can't normally do with a traditional FET. I created a circuit by placing my transistors between the battery and my ammeter, and using my potentiometer to control the voltage going to the sensor leads. I was in pretty theoretical territory, but I did notice there was a measurable delay between adjusting the potentiometer and the ammeter needle moving. This was probably because, depending on the voltage in the cell, it took a little time for the ions in the solution to move from one side of the cell to the other. This is bad news for a transistor, which is supposed to be able to flip on and off in nanoseconds to keep up with radio frequency oscillations. Still, the sulfuric acid solution at least had the shortest delay and the best power transference. I then tested the different shapes of transistor channels I made using this solution. Again, these were uncharted waters, but I found that I didn't need to make the channels nearly as long as I thought for them to remain effective, and that the transistors had a much faster response time the narrower they were, to the point where I couldn't tell with my human senses that there was any delay at all. That doesn't mean there wasn't one though, and narrower channels were also much harder to manufacture. Still, with the best transistor channels I had, I started building a new resonating circuit for my radio called an astable multivibrator. The way it works is that it has two transistors and two capacitors, and they're hooked together such that as the transistors measure the charge on one capacitor, they fill or drain the other, causing them to trade voltage back and forth just like the LC-Oscillator. It does require a power input though, otherwise the capacitors will eventually settle at equal charges, but any inputs at their resonant frequency should be amplified. What's also convenient about this circuit is that I can tune it with my potentiometer instead of using a variable capacitor, since that changes the time constant for the RC part of the circuit. It took some fiddling, but eventually I managed to cause the circuit to generate a buzzing tone in my earpiece that I could tune, same as the LC-Oscillator. I was reminded by the buzzy sound of the tone that the circuit was creating what's called a square wave, or something close to it, because of the way capacitors charge, which is almost immediately with a slow crawl towards topped off. Now I have a decision to make. Which circuit should be my receiver, and which should be my transmitter? I at least know that the LC-Oscillator should be able to produce and transmit radio frequency signals. The transistor radio I'm not so sure about, so I need to conduct some tests. Before doing anything with radio waves, I just hooked the two circuits together, using the LC-Oscillator to generate a signal of a particular frequency, and the astable multivibrator to pick it up and amplify it. I calculated what frequency the LC-Oscillator was running at, and flicked it on and off, or scratched the power contacts, and figured that if I could hear that scratching on the astable multivibrator circuit, that meant they were both working on the same frequency. It took some fiddling, especially because most of the frequencies I was interested in were way above the human range of hearing. I could still detect sounds through the earpiece though, because they were effectively AM or amplitude modulation signals. What this meant was that even though the waves generated by the oscillators were at a frequency I couldn't hear, Scratching the contacts still caused the amplitude of those waves to increase and decrease at a rate I could hear, namely by changing how hard the Rochelle Salt crystal in the earpiece was shaking. In the midst of my fiddling, though, I quickly realized there was a major problem with the circuit, and that was the fact that an astable multivibrator can't actually replace an LC-Oscillator. Yes, it creates an output signal at a particular frequency, but it doesn't resonate. It just buzzes at that frequency as long as you supply it with power, specifically DC, and AC at any frequency doesn't really help. I had to come up with a different solution, but playing with the astable multivibrator at least helped point me in the right direction. Going back to basics, I remembered, again, that the first step in picking up a specific radio frequency requires a filter, and these filters need not be LC oscillators. Another option is called a bandpass filter, which is basically a capacitor and a resistor wired together. And if an input signal oscillates faster than the time constant for that resistor and capacitor combination, then the signal gets dampened and can't pass through. I always imagined it kind of like those automatic door closing mechanisms at school. If you tried to open or close the door too fast, you experience more resistance than if you try to open it slowly. You can also wire the circuit so that it blocks frequencies that are too slow, and put one of each kind together, so that only a narrow range of frequencies gets through to the detector. However, as I said, the signal is going to be extremely faint no matter what, so you have to use an amplifier like a transistor to make it loud enough to detect. The beauty of the LC oscillator simply being its ability to work as both a filter and an amplifier at the same time. The other issue with building the circuit like this is that it's probably never going to be strong enough to work backwards as a transmitter, but that's okay, as it makes the decision easier for me. The upside, though, is that it'll be, ironically, much simpler than the astable multivibrator circuit I was trying to build initially, as it should only require one transistor instead of two. I went through a lot more fiddling and reworking of the circuits, and did manage to get the transistor receiver working off of the input from the LC transmitter, but I eventually ran into another big problem, and that was the fact that the electrolytic transistor channels I made weren't fast enough to respond to signals above 100 kHz. On the one hand, that's kind of impressive for something I built out of charcoal and clay, but still nowhere near radio frequencies. I stopped and racked my brain a little more. The only way to give the transistors a faster response time was to change the shape of the channels, which was beyond my abilities to machine out of clay. However, because they work kind of like capacitors already, in order to give them response times on par with capacitors, I thought, why not build them like actual capacitors? I could just build a regular capacitor and stick some leads in the intervening space between the plates where the dielectric was, making for an extremely narrow conductive path for the power leads, but a very wide path for the sensor leads. I decided to give it a try with my last pieces of spare copper foil. However, given how close together everything was going to be, I was a bit more worried at this point of the power lead shorting than I was before, so I did a little experimentation, compromising the ultimate capacity of the capacitor portion of the cell by using paper soaked in a potash solution as an electrolyte instead of sulfuric acid. The paper helped keep the leads insulated from the plates, and the potassium hydroxide still gave it good dielectric properties. If nothing else, because the potash was alkaline, I expected it to create a thin oxide layer on the surface of the copper sheets to insulate them, kind of like how pouring bleach in a gas tank will cause it to rust, and opposite of how acids are used to remove rust. I spent about an hour prototyping these new transistors, and made several different versions I thought might work, before leaving them to dry and cleaning up for the night. My thinker was overtaxed anyway from all the tinkering and dead ends today, but at the same time, If my brain isn't worn out by the end of the day from designing stuff and doing science, I generally don't feel satisfied. So on balance, I'd say that's a pretty good feeling for me to have. Week 24, Day 4. After my morning chores, I checked on the crystal solution again, and this time I got much larger crystals. They should be easier to work with for the hearing trumpet, but ever since I started playing with these crystals, I had an idea for one last experiment I wanted to try with them. I held on to some of the larger crystals with electrical contacts embedded in them, and redissolved the remainder of the solution. I then carefully carved some very small wooden frames of various shapes. Most of them featured some kind of incomplete partition in the center, the idea being that, while the crystals are piezoelectric, in their natural form they can't flex very much, because they are solid and brittle. However, if I could get them to crystallize into a shape that allowed them to bend and flex across a larger surface area, they would be able to push much more air back and forth, and therefore create a louder sound. I placed these frames in the solution to crystallize before returning to my new transistors, which I was much more excited about. I tested them with the potentiometer and ammeter to make sure they worked, before replacing the old transistors in my radio receiver circuit and testing their frequency range again. I found that some of the transistor variants had a higher frequency range than others, of course, and fortunately for me, the best ones maxed out at around 22 MHz, which was just enough to receive and amplify lower frequency radio waves. As a side note, I accidentally shorted the electrolytic transistors on a couple of occasions, and when I did, I soon heard a sputtering sound and saw smoke or steam rising off of them before quickly disconnecting the battery. I think there was so much power running through the transistors that it was boiling the water in the dielectric solution. Good to know their limits, and that they won't be completely destroyed if I make a mistake like that in the future, or overtax them. Though it reminds me of the time that I accidentally blew up an electrolytic capacitor during a college electronics lab. That's what happens when you reverse bias them. I was almost done at this point. By themselves, the circuits I built could just barely function as radios, but they needed a few more components. Starting with the transistor, I needed a big antenna. Fortunately for me, I'd already been provided one by the US military, namely the remains of the radio mast down at the bunker. All I had to do was make the requisite electrical connections. It would need power, which I could provide using the battery, but I couldn't be there to constantly tap out SOS, so I needed a way to automate the transmission of a message. The only way I could think of to do that, without wasting more wire on a motor, was with another wind turbine, so I pulled out my axe and cut down some bamboo and sticks to start building one. I gathered a little extra because the radio would need to be outside the bunker with the wind turbine in order to work, so it would need some kind of cover to protect it from the elements. When I was done with the turbine, I stopped for lunch before building a little hutch to cover the transmitter parts, giving it some legs and a frame to keep the electronics off the ground, shingling it with banana leaves, and coating the whole thing in latex just to make sure it was 100% waterproof. Next, I got some cord and some wood, and built a couple of pulleys that connected to the turbine. I then built a little hammer, like the ones I built for the music machine, with a sort of V-shaped slot in one end, which pressed down on an electrical contact in the LC-Oscillator circuit, like a telegraph key. I then started tying and adjusting knots on the pulley cord to program in a message in Morse code, which will basically be a perpetually repeating SOS followed by the island's coordinates. It's a good thing the survival manual from the life raft came with a little booklet with a Morse code key in it, because that was another piece of vaguely scientific trivia that I never bothered to memorize. There was a slight problem with this plan, though, because I knew my latitude from measuring the elevation of the sun and stars, but could only guess at my longitude. For this, I needed to know what time everyone else's clocks were set to in this area, and how far off that was from the time on my sundial. The only way I was going to be able to learn that was by listening to them talking to each other over the receiver radio, so I started working on that next. I hooked up an extra transistor to the receiver circuit and built a second potentiometer that I could use to control the volume. Fortunately, this circuit didn't require a lot of power, so I could use a battery from the emergency radio to run it, at least for a while. Next, I needed an antenna, and fortunately, any old piece of wire would do for the job. Once I had it all wired up, I turned it on and started listening for radio stations. Most of what I heard was just noise or incomprehensible tones that I could only assume were digital. However, when I finally did pick up a station I could understand, around the 10 megahertz range, it was kind of a shock to my system psychologically, because it's been so long since I've heard a human voice other than my own. It was comforting in many ways, and yet somehow also creepy in others. Perhaps this was from knowing that I could hear them, but they couldn't hear me. However, with any luck, that will soon be remedied. A lot of the stations I was picking up were in French. From my previous flight path, I think I was flying in the vicinity of Papua New Guinea, so maybe they speak a lot of French there. However, there were also a handful of English-speaking stations. Even without them, I knew just enough French numbers to be able to tell when someone was calling out the time. Eventually, I picked one up, saying it had just turned about 4 p.m., so I checked my sundial in the courtyard to measure the difference. I knew that Greenwich, England is considered to be at 0 degrees longitude, and there are 24 time zones, one for each hour of the day, going all the way around the Earth 360 degrees. So each hour difference from Greenwich is 15 degrees. Each minute difference is a quarter of a degree, etc. The sun rises in the east and sets in the west, so I knew that a time zone further east was going to be later than one further west. If memory serves, and my estimates are good, I was just about on the opposite side of the planet from England, 180 degrees difference. So if it's 4 p.m. here, it would be 10 p.m. there, plus the small difference I got from the sundial, about 172 degrees west. Once I'd calculated my coordinates, I programmed this last piece of the puzzle into my radio transmitter and carefully moved the whole kit and caboodle over to the bunker, though I walked along the beach because I didn't want to leave a trail through the jungle. I approached somewhat cautiously, as the place still made me nervous, even though I was pretty sure no one was around. I decided to situate the transmitter close to the antenna, but in an open enough area to catch a breeze from the ocean, in addition to being in view of my periscope, and concealed enough to not draw immediate attention from anyone walking up, as it'll kind of give away that I'm here before I can hear the wind chimes through the acoustic telephone, which I gave another test while I was there. There's a strange juxtaposition between the calming sound they make and their nervous purpose as an alarm. Naturally, these were all factors that were very difficult to balance, but eventually I found what I consider to be an acceptable compromise between them. I hooked the radio transmitter up to the battery, covered it, and let it run. I knew the windmill wouldn't run it constantly or at a consistent speed, but I considered it better than sitting there and tapping all day. I scraped away a little bit of the rust from the antenna using a rock and tied the transmitter wires to it. Finally, I set the frequency. I couldn't remember much from my short attendance to the radio club back home, as I was always more interested in the physics of radios than talking to strangers across the world, so I wasn't sure which frequency to transmit on to be heard. I at least knew that people were talking and listening on the 10 megahertz range, so I set my transmitter to that frequency and left it to run. This is lower than many radio communication frequencies, and should therefore travel further, especially over the ocean, where there are no obstructions, and at night, when the ionosphere causes radio waves to be reflected. However, even with all these upsides, my transmitter will probably have a poor range because of its low power. If I'm lucky, this thing may be outputting 1 or 2 watts, which may give me a range of maybe 5 miles during the day and up to 10 miles at night. Perhaps more because the salt water is conductive. Still, it's better than nothing. I felt a strange sense of finality to what I was doing there. Like I've set the gears in motion, and a boat might as well be on its way to pick me up now, and all I have to do is wait. On the one hand, it's a relief to think about being cold again, drinking Coke and eating cheese again, to sleep in my own bed again, and to hear my family's voices again. And yet, I can't help but also feel a twinge of regret, which is much larger than I would have otherwise expected. Much larger than it reasonably should be. I've built so much here, and although it's been hard, almost unbearable at times, it's also been a blast, literally. I've made things here that I never could have dreamed of doing at home, and it's been stimulating in a way that I've never felt before. There's a sense of pride, of self-confidence, looking upon all my creations and inventions here that I never had at home, where the best I could do was write, draw, or dream of such things. And I'm going back to that now. The party's over. I'm going back to work, probably delivering mail again instead of engineering. Back to paying bills and shopping for groceries instead of just picking them up off the ground. And in a way, I'll go back to being almost as alone there as I am here. I shook myself from my somber reflection, though, because there really wasn't anything else I could do. I have to get out of here before the smugglers come back, otherwise I may be in danger. And I have to get out of here eventually, because I just don't have the resources here to finish my life's work. Furthermore, I still didn't know if the radio was working properly. I returned to base and set up the receiver radio using my leftover wire as an antenna, which I wrapped around a piece of bamboo to hold it straight. While I went, I considered the fact that I probably could have gotten away with a simpler crystal radio by using a piece of galena as a diode, but I would have had to power it from a much longer antenna, and this way I didn't waste nearly as much wire. Though when all the capacitor and transistor components are accounted for, perhaps more total copper. Hard to say. I spent some time tuning it to the approximate frequency I set the transmitter at, until I could hear the faint buzzing of the SOS signal mixed in under the garbled voice of a DJ. It was definitely working, and again, I felt that strange simultaneous sense of relief and dread. I didn't know what to do with this feeling. So I sat on the beach until the sun set and got ready for bed as usual. I brought my mattress up onto the roof of my house for a while to watch the stars in the cool of the night, occasionally picking up my telescope for a closer look as I drifted off to sleep. Almost felt like I was looking at them for the last time. Week 24, Day 5. When I got up in the morning, I decided there was no point in sulking about going home, or just waiting around on the beach for a boat to pick me up. If I'm having fun here, I might as well make the most of it while I can. This gave me something of a renewed vigor for my projects, and thankfulness for the resources I did have, especially as I proceeded with my morning chores. I started by getting some clay and making a cover for my transistor radio, to not only protect the delicate electronics inside, but also to make it easy to move around. I also left holes in the resulting pot for the volume dial, frequency stepper buttons, the speaker, and the antenna, so in the end it would look like a real old-timey radio. Since I had more or less finished the radio project, and a little earlier than I would have otherwise expected, I considered what else I could do with this week's theme of electricity and electronic circuits. One major issue that occurred to me was that the transmitter and receiver radio's batteries were going to run out eventually, so I needed to make more. At least the transmitter's battery was rechargeable, but I thought it would be nice to have a spare that I could charge and swap out, like my lawnmower batteries back home. The receiver, however, didn't need nearly as much power, so I thought it would be nice if I could make some smaller batteries for when the emergency radio's battery inevitably wore out. It occurred to me that I could make some simple cell batteries the same way I made the copper foils. Just dip a bamboo stick in some molten metal, though this time I'll leave the partition in place, so that it can take the shape of a nice little canister. As for the chemistry of it, my understanding is that you can use almost any two metals and an electrolyte as a battery. It's just that some combinations produce more voltage than others. And if there was one thing my experiments with the lead-acid battery taught me, it was that the voltage produced is a function of the chemical reaction in play, not the amount of material, which was cool and unexpected. Even two of the same metal should work, as long as one side holds the oxygen, again, like the lead-acid battery, which can then be recharged by electrolysis, which is another bonus over regular batteries. These facts were good news for me, because I was running out of copper, so it gave me a potential application for my light, soft mystery metal from a few weeks back, which I was beginning to wonder might be zinc, as it's tarnished aggressively into a white powder. Definitely not aluminum, and I'm not familiar with any other low-density metals that react like that. Couldn't be magnesium because it would have burned when I tried to melt it. I decided to do a little experiment first, cutting the probably zinc so that it had two pieces, one covered with oxide and the other not. I then played around with putting them in solutions of different acids, bases, and salts. Finally, I connected the pieces to my ammeter and a resistor to measure the voltage. I didn't expect particularly large voltages from these cells. The best I could achieve was about 0.8 volts with a potash solution, which I still found a bit impressive, about half that of a traditional alkaline battery. Armed with this information, I fired up the kiln and started making batteries, first grinding several differently sized forms of bamboo scraps using the grinding wheel, and then dipping them in the liquid metal like I planned, until I used up all but a tiny puddle of zinc left at the bottom of my crucible. Once I had all my little zinc pots of various sizes, I nested them together kind of like Matryoshka dolls. The idea here was to create as much surface area as possible inside the cell to make the most of its volume, just like I did with the lead-acid battery. Like I said, it wouldn't change the voltage on the cells, but it would increase how much charge they could physically store. I had to finagle them a bit to make sure that they slid together, open end to open end, without any of the metal canister walls touching. In the meantime, I boiled down my potash solution to concentrate it, but to keep it from leaking out, I remembered hearing that the first dry cell batteries used starch as a binder to keep the electrolyte as a paste, so I mixed in a little taro flour until I also created a paste, which I then poured into the canisters and gently pushed them together. To keep any additional material from leaking out when it was finished, I used a little latex around the rims to both seal the electrolyte in and keep the canisters electrically insulated from each other, otherwise the reaction would not take place. As a final touch, I slid the completed battery inside of a bamboo sleeve because I could feel how weak the thin metal walls of the canisters were, and I didn't want them to break by accident if I dropped them. This also made it easy for me to mark on the outside of the canisters which side was the negative terminal and which was the positive, though technically with these batteries it could be either. I then stopped for lunch and tried to think about a few other things I could do with these batteries. Besides the radio, the only thing I could think of that would be particularly useful was a flashlight, especially to replace the oil lamp in my headlamp, because no one likes having a Molotov cocktail tied to their head, especially when they're playing with explosives. The trick was making a light bulb, and again, glasswork was not my strong suit. Still, when lunch was over, I decided to give it a try, gathering and purifying some sand before firing up the kiln again. This time I took a small hollowed out piece of bamboo and coated the end with clay so it wouldn't burn when I dipped it in the molten glass. Once I had a little glob on the end, I blew a little into the bamboo pipe to create a bulb. I remembered seeing videos of glass workers rolling their glass bulbs on a flat surface to try and get the shape they wanted, and even rubbing it with what looked like a rag at times, but I didn't want to take the chance of burning myself today. It was like trying to work with taffy or caramel, but hotter than HE double hockey sticks. And at first what I made was more like a bottle or a vase than a light bulb, but I managed to cut it off, and decided to set it aside just because it looked kind of pretty. As I moved on, though hot, frustrated, and occasionally burnt, I managed to create a few different glass bulbs. What I found easier to do was to draw the glass by dipping the end of my pipe into the melted sand to pull up a thin tube, which eventually closed in on itself at the end due to surface tension, which I could subsequently blow to make a thin-walled bulb. Since I didn't know what bulb design would be best or easiest to make, and since I expected to break many of them, I made several, some as bulbs, some as tubes. While I was at it, I made several longer glass tubes of various sizes, because I found them the best option for various kinds of glassworking experiments back home, and I really didn't want to have to bother with this again if I could help it. Then again, I'm still going to need to use the kiln if I want to change their size or shape later anyway. Still, the tubes will make for an easier starting place than amorphous glass. Now it's time to move on to lighting the bulbs, and I basically have two ideas for how this can be done. The first is the classic incandescent bulb, where a current makes a thin filament white hot. But I don't want to risk wasting any of my wire if the current causes the filament to burn out. They're also very energy inefficient, wasting most of the energy that goes into them as heat. The alternative is an arc lamp, which uses two carbon rods very close to each other, between which a bright electrical arc is formed. I think these are a bit more energy efficient than an incandescent bulb, but I think they also require a blast of high voltage to get them started, which would require a complex ballast circuit that I'm not entirely sure how to make, other than that it requires an induction coil. So, as much as I hate them, the incandescent bulbs are probably my best option at the moment. And if I remember correctly, Edison managed to make his light bulb filaments out of thread. In my case, I think I can use a bit of carbonized bamboo cord, which should be stronger and less likely to break if there's a hot current running through it. The higher resistance of the carbon compared to copper should also mean that I can get away with shorter overall filaments. Still, I don't know how long the filaments need to be, so I'll spend the remainder of the afternoon experimenting. I made several filaments of different lengths, each wrapped around a small stick or the like, with varying numbers of turns to make the filament coils. Some I slid into the glass bulbs, and others I slid into the glass tubes to see which ones worked better. I then capped off the ends of the glass tubes with clay, the glaze of which I expected to meld with the glass and the bulbs under heat, and I made sure there was a pair of wire contacts sticking out the ends. I put just a drop of methanol in each bulb, the idea being that the methanol would burn up the residual oxygen in the bulbs once I started cooking them, instead of burning up the filaments, protecting them from being burned up and allowing them to turn mostly into pure carbon. That was about all I could do before the end of the day. Week 24, Day 6. I put my radio cover and bulbs in the kiln in the morning before starting on my daily chores. Once I was done, I worked on adapting my headlamp to accept the light bulbs when it came time for testing. I removed the oil lamp, and fortunately for me, the parabolic reflector in it didn't really need any modifications. However, I did use some bamboo to add an adjustable lens mount to it, so I could focus the light from the lens, either to a distant point or to spread it out so I could better see my immediate surroundings in the dark. It did cross my mind, though, that this might not be necessary if I don't expect to be here much longer. Still, better to prepare like I'm going to be here for the rest of my life, just in case. I also attached some capped sections of bamboo to make battery holders for the lamps. The lamp itself would be heavy enough, so to balance it, I put the battery pack on the back of the headband, even though it meant I needed to use a little more wire. I couldn't think of any more fun I could have with electricity after that, so I decided to just work on other little projects I'd fallen behind on. Got a little head start on my beginning of the month maintenance day since it was coming up anyway. I grabbed another lens from my stockpile and carefully ground and polished it into a near hemisphere. Not as perfect as if I'd had a dedicated grinding head for that purpose, but it was good enough. This'll function as that fisheye lens I wanted for the bunker periscope. I'd also maxed out my latex storage, so I fluffed up a batch to make one more mattress for the panic room. I almost forgot again that my second sheet for the dynamo was finished, so I removed it from the electrolysis cell, installed it in the dynamo, and reset the cell before having lunch. When I was done, I removed the parts from the kiln and let them cool. I then started assembling my radio parts inside the cover, and I was really jazzed with how it looked. However, when I turned it on, I noticed how I wasn't picking up my SOS signal anymore. I checked the bunker through the periscope to make sure it was safe before walking down there. I needed to install the fisheye lens anyway. There was nothing wrong with the transmitter itself, the battery just ran out, which I suppose was to be expected after all the work I put it through in the course of my experiments this week. I took it back to base with me and planned to charge it overnight, another setback for the dynamo project. While I was in the workshop, I decided to build a battery charging rack for the zinc cell batteries too, which basically amounted to a frame with a wire rail running across the top and bottom that I could just slide all my batteries into at once. I had to be careful to add a resistor to this circuit though, so that the batteries would never get charged to more than their maximum capacity of 0.8 volts. Otherwise, the electrolysis reactions inside them may create gases, like oxygen and hydrogen, which would cause the batteries to burst or even explode. Once I had everything wired up, I stole a little more electricity from the dynamo to test my light bulbs, which I would have had to run on the same voltage as the batteries anyway. However, this caused the bulbs to not produce much light, at least of the ones that survived the firing process intact. I remembered how a regular flashlight tends to have the batteries stacked on top of each other, which stacks the voltage, so I used the voltage from the lead-acid battery instead. This destroyed a lot of the shorter carbon filaments, which were too brittle and couldn't handle the expansion from heating. Still, I eventually found a handful that survived and produced a useful amount of light. I made a little bamboo plug and socket for one of them, and finished installing it in my headlamp, which I took down to the panic room to give it a proper test in the dark. The combination of both the lens and the glass from the bulb caused the light to again take on a slightly greenish tint, but for the most part the light was pretty impressive and much better than the old headlamp. The remaining bulbs I held on to for later projects. It would be nice to install electric lights everywhere in the base, but I hardly have the power available to charge my batteries, let alone electrify the whole base. I would prefer something more efficient than incandescent bulbs anyway, if possible. I had a couple more hours to kill at the end of the day, but again, I wasn't really sure what to do with them, so I started tidying up early and chilled out for the evening, turning on the radio and listening to different stations until it was time for bed. There was a lot of reggae music, which I didn't enjoy at all. Unfortunately, it reminded me of all the things I don't look forward to dealing with again on the mainland. Week 24, Day 7. It's my Sabbath today, and this time I could actually confirm that it was the right day on the radio. After I finished my morning chores, I settled into my office and turned on the radio to listen while I did some writing. However, I had a last-minute change in plans when I came across a Christian station broadcasting in the area. I suppose this makes sense since Polynesia has one of the highest Christian populations, proportionally, of anywhere in the world. I caught some classic hymns, and I started aching for home again, but I noticed it wasn't for the home I left as much as it was the home I grew up with. Not the world as I left it, but a world I seem to have lost long before, if that makes any sense. Then a sermon came on, and I started taking notes, almost reflexively, like I used to during Dad's sermons. It had frankly been a long time, even before I got stranded, since I'd heard an actually good sermon, and fortunately for me, this particular pastor has apparently begun a series going through the Bible chapter by chapter, verse by verse, just like Dad did. He didn't go into nearly as much detail and exposition as Dad did, but it still reminded me of him, and I started to cry, even as I continued to automatically transcribe what I was hearing. I'd been so busy surviving and playing around with my inventions here that I'd all but forgotten God. I'd certainly forgotten how much I missed having a Bible around, so I took one of the blank books I made and started a new project where, for as long as I'm here, I will transcribe the books of the Bible that I hear over the radio. Of course, that would take me years, and either fortunately or unfortunately for me, this station apparently didn't just read through the books of the Bible on Sundays, but every day of the week, sometimes repeating themselves later in the day, for anyone who missed the early sermons, I guess. I appreciate the thoroughness, and the fact that it's apparently a read through the Bible in 1 year series, which means they read about 3 chapters a day, but my hand was already cramping up from trying to keep up with the narration. If I want to transcribe the whole Bible, I'm going to need a faster way of writing, and some way of recording the sermons, because I'm not going to have time to sit in front of my radio all day every day to write, especially not at the rate of experimentation I've been doing lately. The recordings should probably come first, as I should be able to catch up with them later if I need to. So I basically need to make a phonograph, starting with the records. I can make these fairly easily as simple clay plates, but the tricky part about their manufacture will be to make a consistent spiral groove from the center to the rim for the needle of the gramophone to sit in, one that doesn't cut back into itself or waste space by moving to the rim too fast. I found that I just had to do this carefully, starting slow and trying to keep a steady hand as I used a fishbone needle to cut grooves into my clay record. I had to start over a few times because steady hands were never something I really had. More like fat butterfingers. Once I had a plate that appeared mostly defect-free, I set it aside to dry with the intent of using it not as a record, but as a mold, since I don't want to have to cut another record like that again. While my hands were dirty, I made several more clay plates in preparation to be turned into records. I don't know what material I should be using for actually cutting the records with yet, but I thought I might be able to use these clay discs as a base, which I can coat later with something that's easier to record onto. I left the record mold out to dry while I worked on the rest of the mechanism, which was actually pretty easy and used mechanisms I was already familiar with from previous projects. I started by constructing a bamboo frame for the turntable and cutting a rubber band from the scraps left over from making the spare mattress the other day, in order to make a spring which I wrapped around an axle. With this, I could just wind up my gramophone and let it run, but I had to add a flyball governor to it so that it would rotate at a consistent speed. A pull cord completed the mechanism, making it easy to wind up. I then prepared some more clay discs with holes in them, one of which would be fixed to the axle, acting as the turntable, and the other as a weight to sandwich the record down and hold it in place during recording and playback. This more or less completed the gramophone mechanism, but I wasn't done yet. The sermons I wanted to listen to appeared to come on at specific times of the day every day, so I worked on building another clock mechanism, which I installed underneath the gramophone turntable, specifically using another spring mass oscillator design because it was a little simpler and more compact than using falling weights like the grandfather clock. I also rigged the little timer mechanism so that instead of ringing a bell, it would start or stop and catch on the gramophone, causing it to stop or start recording at specific times of day, though it'll be important for me to make sure that this clock is accurately calibrated. This project caused me to get in a late lunch before splitting some bamboo and covering the gramophone frame so it looked pretty, giving it a coat of varnish as I went. To one of the leg pieces of the frame, I attached a bamboo arm that rotated back and forth freely to cover the grooves in the records, and while I considered this to be a potentially good use of that one hearing trumpet I made but didn't use, I realized it would just be easier to connect the radio itself to the stylus of the record player, and use it for both writing to and reading from the record. That said, I was going to need a stylus, and I was glad at this point that I'd experimented with those molded Rochelle Salt crystals the other day. They were just perfect for the stylus, and one fit perfectly inside the bamboo arm. Instead of attaching a diaphragm to the crystal, all I needed to do was attach one of my bone needles to act as the stylus. Although it wasn't strictly necessary, I attached the spare hearing trumpet to the gramophone anyway, and installed another piezoelectric crystal and a rubber diaphragm for it to vibrate. Part of this was to complete the iconic gramophone look, and the other was to let me listen to what was being recorded, so I could make sure the machine was properly calibrated. It would also give me a means of dictating messages, should I have so desired. I tested that the stylus was working properly by rubbing my finger across it and hearing the sound out the hearing trumpet, the crystals by themselves producing a one-to-one transfer of energy from the stylus to the trumpet. However, it also seemed to work when I hooked it up to the radio, as I can hear the transmission out the trumpet and feel the needle vibrating against my finger. I then added a simple switch to the wire hookup between the radio and gramophone, and called it a night.
Hey there, Islanders, DJ Myers here with all the bloopers you're looking for because you need to loosen up a bit, man!
Alright, we are live at 5 and I'm ready to jive. Let's see how recording with these new headphones works. The dynamo isn't even close to being finished, but I don't need to let that stop me from building some electronics. Head voice.
Head voice! Gotta speak in my head voice. That'll get the rumbles out of the recording.
Shaking the electrons in the antenna so hard that they create radio waves. I decided to smoke. Hold on. Alright, I guess it's just easier to stand. Back to it. Where was I? So the compass needle. I tried to think back to my college physics. Alright, need to breathe before I continue speaking. Since the same voltage as a real lead acid battery. Pause for edits. I carefully wedged so I couldn't get a good idea of how much weight it was actually holding. Air. I need to remember to breathe. Which is in turn also affected by any resistance in the current. To increase the resistance in the current with varying numbers of turns to make the filament with varying numbers of current, this is called the circuit's time constants. Words. What even are words today? Where's my nose stuff today? Called an astable multivibrator. I can't remember if I fixed this section yet, so I'll continue recording until I find out.
Like I need some horseradish or something.
I was in pretty theoretical tech. The upside though is that The upside, though, is that you can't see it, but I'm standing like a flamingo, compromising the ultimate capacity of the capacitor portion of the cell. I wonder if that messed it up. If nothing else, because the potash, and tied the antenna wires to it, and tied the transmitter wires to it. I have to stop and make some corrections. The best I could achieve. I didn't expect particularly large voltages from these cells. There's no right way to say it. I used a little latex around the rims of both to seal the electrolyte in. And if this again. Coke, I love you, but you make me burp. I also attached some cap. It's hard to say. Why is that hard to say? It had frankly been a long time, even before I got strangled. What? Strangled? No. The recording should probably come first, as I should be able to bump the mic. Ka-chunk. Hey there. Thanks for tuning in. I think I broke my personal record for video length with this one, so I appreciate you sticking around. The radio is currently transmitting my location on all frequencies, so if you want to see if it manages to attract a rescue boat, you can press the subscribe and bell buttons to get notified as soon as my SOS is received. Every little bit of engagement tells the algorithm to relay these messages to more people, and each view brings me a little closer to getting out of here. It's far from perfect, though, and I'm not charging for these videos, which means the algorithm doesn't push them as hard. So it would really help me out, more than anything else, if you could share this video with someone who you think would enjoy it. And since you apparently enjoyed it enough to listen to me prattle on about electronics for over an hour, there's a like button you can press to say so. I appreciate the positive affirmation. There's also a dislike button you can press if you have a negative opinion of the video, but I'd find that quite shocking. Also, if you want to chat about your own stories and perspectives on the episode, maybe about some DIY electronics projects you've worked on and were proud of, or any tips or tricks you learned along the way, or if your name is Kenneth, what the frequency is, feel free to share it in the comments down below. I genuinely love to hear them, and I'm always open to suggestions and corrections. That said, thanks again for listening, and hope to see you here again next week.